So what we started at the last lecture, and what I want to continue now is this idea of entanglement entropy, namely that you have a quantum system. A quantum system means a state described by a complex vector. But then you decide that of this complex vector, you want to not see some parts of its information. We were talking about systems A and B, but just the same, you can think about just forgetting or not seeing some degrees of freedom. And as Landau realized, you immediately now not in a vector state, you in a matrix state, described by a density matrix. And right a few months after, von Neumann realized that the state is characterized by entropy, which is zero for any pure quantum state. So now what I want to give you, and it's surprisingly rare, I won't find any textbook which gives it in more or less original von Neumann form. Von Neumann form is like a book. I mean, it's definitely long. It's 1927. Quantum mechanics appeared just a year and a half before that, right? And von Neumann was like Szilard. He was his older friend from the same gymnasium at Budapest. He was young a few years. We were the students, and they lived in this time where there was feeling like something happened, but you need a friend to tell you this is important. And Szilard was a guy who kind of created modern information theory, and so von Neumann, who was of course a genius, much grander scale than any of his friends from this gymnasium, but they immediately recognized it. So what was his argument? Von Neumann, again, like they were all, Boltzmann grandkids, right? So what they were thinking about is essentially, they were any thinking started from gas in a box. Okay, they were from Austro-Hungarian Empire, right? They were Jews from Budapest. So von Neumann said, imagine that you have n molecules in a box, but there is some quantum variable which characterize every molecule, and it could be in a state A or it could be in a state B. And those are orthogonal state. Orthogonal state means that they somehow behave differently. There are some operation, for example, you have two polarization of light, right? So this polarization comes through polarizer and you see the image in this, and then you have a polarizer and this won't come through polarizer, right? That essentially means that they are orthogonal. There is some physical operation which clearly distinguishes it, right? And of course, when there is these molecules, and we know about every molecule in which state it is, and we know its position, whatever, so it's in a pure state. But now, said von Neumann, we don't distinguish which molecule is in which state. So the only thing that we now know, as we prepared this state, we know that this Pn is in the A state, and 1 minus Pn is in the B state. And that means, say, that Landau said, that what you essentially describe the system, that every molecule is characterized by a matrix, density matrix, in which you take this and you add this element. So it's a diagonal matrix, and on the diagonal you have these elements. Okay, that's essentially what is a density matrix. And for the whole system, you just take a tensorial product of it in the power n. Right, this is your density matrix of the whole state. Okay? And now how von Neumann associated an entropy with it. It suggested a procedure. It's a very, very Maxwell-Boltzmann way of thinking. A procedure so that you can really show how you can bring the system into zero entropy state, and then the heat that you release during this time would be temperature times entropy of the system. So you can say, let's double the volume, and of course take a piston. What else we know what to do? But this piston would be impenetrable for A, and that piston would be impenetrable for B. Okay, it's like polarizer. Okay, so we have two states, so which means that now you can push this up to Z, you can push Z after Z, right? And so now you have all A's here and all B's here. So that's your state. You have a double volume, and you have B's and you have A's over here, right? Now, still, what you were doing is still a manipulation, which was dynamical manipulation. When light passes through polarizers, there is nothing kind of wiping over. Just some light is reflected, some light passes through. It's a purely dynamical procedure in optics, or what we call unitary in quantum mechanics. It's preserve all. Now he says we want to return a system to its original volume, which means that we need to compress. Now our volume is twice larger, right? But also he says that because there were different number of molecules, there are different concentration in this part, right? Because if P is not 1/2, then let's say P is larger than 1/2, then there is more molecules in this volume than in this volume, which means that the concentration here is larger than this because volumes are the same, right? So what do you say? Now let's take this piston back and now push it in the backward direction at P times. And here we take this and push it back 1 minus P fraction. Okay? Now, when we compress at P times, and this minus P times, it creates the same concentrations. So now it creates the same concentrations, and we have original volume over here. Okay? And now he says that now let's apply magnetic field and rotate polarization of A to the polarization of B. It's purely, I mean, orthogonal does not mean that you cannot make this light with this polarization into this polarization. You can run it through a crystal with a, what is called optical activity. There are some people from optics who use, but you can use, assume that you have spin, right? And so you can just apply magnetic field and turn spin. So you can turn A into B and then remove this thing. So what you get eventually is that all molecules are in the same states. In the same states, there is nothing to know, and you know in which, because you rotated A, and you have the same original volume, but this is zero entropy. Zero entropy with respect to this AB mixture, right? There are some other degrees of freedom. How much heat we released? Well, we compressed. You remember? It's like when we did Landauer argument. So when you compress and you are in a final temperature, then you would be releasing a heat, which would be, of course, T S of P. So your entropy is S of P. You actually don't need temperature, just for the sake of argument, because you were asking what was the entropy that you eliminated, bringing to this zero entropy state, and this was S of P, which is P log P plus minus 1 minus P log 1 minus P, which of course is the same as the trace of rho log rho, where rho is this matrix. Okay, it's a relatively short explanation of, and it really took me some time. First of all, I didn't find it anywhere, so I've read von Neumann like 20 times. And so if you're interested in it, I advise you to read von Neumann. It means that I've hidden from you a lot of brilliant details and arguments, etc. But I really don't want to put it into the long thing. But I think that this is essentially the essence. Okay. So you see, in this case, it's not A and B like separated system, but it also tells you that just by tracing out or forgetting some quantum information is characterized by an entropy, and of course this entropy is essentially a Gibbs-Shannon entropy of the P distribution, but in this case the state is indeed a matrix state. Okay? Questions?
Was it measured somehow, like the transition from like quantum states to?
What we measure is the heat released in the system.
And those experiments that.
Yeah, experimentally. You want to check all this stuff experimentally. So as you measure how much heat you produce by compressing these things, and this heat would be a function of this number P. Okay, so you can change this number P, which again you can run your things through polarizer or through whatever, which means that you can mix them, and then you can change how much heat you generate, and that's your test of von Neumann entropy. And of course, people did it many times. Okay, that's another PhD part of a PhD. Okay, good. If this is okay, then what I really wanna finish this quantum mechanical, quantum statistical part and go to relativity, as I promised you, that what we're now doing, these lectures, and partially maybe the next one, is the fundamental limits of uncertainty. So now I want to give you, without derivation, a formula which is the general uncertainty relation, quantum uncertainty relation. And if you want me to derive it, we can make tomorrow a tutorial and I'll derive it. Take about half an hour maybe to derive it, but now I'll explain. Okay? So what it's all about. So consider that we have some kind of a mixed state, namely that it characterized by the matrix rho, and it's a density matrix, and it we can measure about it different things. For example, there is an observable, which means an operator. You can think about coordinate or momentum, and so you can measure in this state what is the momentum of the particle, and you can say that there is some kind of a this by acting by this operator on your rho, you create some kind of a rho x, and this rho x could be now expanded into the basis of a different x state. Well, you can say xi, so there are different states having eigenstate of operator x. They have different eigenvalues x, and they all characterized by their p or p of x or p of xi, right? Which would mean that there is a probability distribution of having different values of x. So if in this state you start measuring coordinate, you would get different values. Maybe sometime, maybe it's in a pure state on x, so this probability is delta function, okay, which means that its entropy is 0. But generally, you can have a superposition of states with respect to x, and then you would have some distribution. So you have some probability distribution of different value of x, and it corresponds to the usual. So every time here is Latin here, it means that this is just the usual Gibbs-Shannon entropy, which is essentially the minus sum over x, p of x log p over x. Okay? So far, the only quantum here was the fact that in classical, X could be something which could only exist in one state, and in quantum case, you can have the whole distribution because it could be in a superposition. Okay. Now, the same thing you can do about Z. So you have another observable Z, which again generically is not computing with X. And so you can do all the same thing, and you can define the respective S of Z. Okay. On the other hand, because you are in a matrix state, and in a matrix state, I mean, if it's a matrix and it has, and it's not one line, then this would be zero because the trace would be unity. So there is S of rho. Now it's Greek. When it's Greek inside, it's for Neumann. When it's Latin, it's Gibbs. Okay, just it's kind of standard definition in this side. So this is a trace of rho log rho, which is understood as a trace of the matrix. Okay? In what connection these things are? That's essentially the question. So before I'm starting telling you stories, try to imagine. So I'm about to write some relation between these quantities, right?
Which quantities?
Okay, so far what I said, you are in a row. There are many other things except X and Z in this row, but in particularly it's also about X and Z. Okay, but it could have spins, God knows what. Okay, and then it says that you can always define just in this. It's a matrix, and in this matrix you can take a trace of rho log rho. You diagonalize it, and then it will have a diagonal matrix in which some other p values would be, but its dimensionality could be huge comparing to X and Z. It could involve some other things, right? It's always in quantum mechanics we're talking as if we're talking about vectors, and but we're talking about some huge spaces of which you don't even want to think how. But in this respect, this is a well-defined quantity. We just computed it for qubit in the last thing. Okay, and so now we have 3 entropies. Those are 3 numbers, like 5 bits or 10 to 23 bits. This is just numbers. So you have 3 numbers: this number, Z number, and Z number. Okay, but could we? I'm not trying for you to guess what I'm about to tell you. Is there will be some relation of a type of equality or inequality? Are these 3 numbers enough, or there something else must be in this relation? Let's start from the think that is there something else, some other number that must be involved in this entropic relation which I'm about to write?
The joint entropy of X and Z? Like how much they're correlated?
Well, there could be, in principle, yeah, there could be something which you really want to make it a type of mutual information statement. That could be a joint entropy. But also, let's say, if would we be in a pure state? In a pure state, S of rho is 0. It's not a matrix. Is there any relation about S of X and S of Z that we already wrote in the last lecture? Well, you can look in your notes, absolutely. Or you can look if somebody has a book around. So what kind of statement we made about coordinate and momentum and entropies of their distribution?
The uncertainty.
Uncertainty, but not Heisenberg, but Deutsch, like upgrading Heisenberg uncertainty about variance to the more general statement of uncertainties about entropies. And in particular, we say that S of P plus S of Q, you remember, were larger or equal than the logarithm of D, where D was the quantum dimensionality of Hilbert space, or we also say that this is essentially larger or equal than maximum of a P and Q, a product of P state, Q states. Or when we you can generalize it for X and Z, we were saying that this was log X, Z, their mutual degree of non-orthogonality, let's put it this way. Because this degree of non-orthogonality is directly related to the degree of non-commutativity of these two matrices. When two matrices commute, you can always diagonalize them by the same set of basis vectors. Okay? And if matrices do not commute, then one matrix is diagonalized by eigenstates, which are generally non-orthogonal for all the eigenstates of other matrices. And this degree of non-orthogonality or overlap is what enters, and in particular, the Heisenberg relation is what we said is a mutually unbiased when the x zx is just 1 over d, namely that any vector on a projected the same on a d other vector, any vector x is more or less with uniform probability could be projected on the other vectors, and this then would be 1 over d, because when you sum over d, you get unity, right? And so that was a quantum mechanical uncertainty relation for usual non-commuting variables, okay? And this was bound on the sum of the entropies. Of course, this differential entropy, if you do these functions, they are defined up to a constant. But what is important that when you decrease your uncertainty about one variable, you must increase your uncertainty about other variables. That's why it's called uncertainty relation. Now what? When we have this? Would this something which enters this relation on this or that side, or there will be something which would be in other way, bounding something here or there? What would be your guess?
The S of O is like bounding from both the sum, maybe.
Where you want, okay, so we have this relation, right? Where you want S of rho, here with the sign plus, here with the sign minus, or here with the sign plus, or on both sides, then it would cancel out. I mean,
on the left.
So you want it on the left with which sign?
With minus.
Which means on the right with a plus. That's how you make discoveries, actually. Right? You try, then you see it looks idiotic, then you try it with the other side, and it's now less idiotic. Okay. So what you are saying that this is plus S of rho, and congratulations, you are right. This is the general quantum uncertainty relation. And trust me, every genius which make a discovery usually made it this way. Like here, let's put it there. No, it must be no. Okay, now it's clear. Particularly read Planck's short, I mean this 2 or 3 pages, his paper about entropies and the birth of quantum mechanics. So this is a very natural relation. It's not easily derivable. Namely, if you want me to derive it, you send me, well, you tell me now, and we'll see if there will be more than 2 people, then I'll give you a tutorial and derive it. It will take half an hour. Okay? It derived by monotonicity. Remember what is monotonicity? So if you have several variables and then you trace out some variables, that generally your relative entropy decreases. It's kind of state. Everything is done through relative entropy. But by itself, it's very intuitive. And you see, you design it out of nothing, just common sense. And it tells you again that whatever you have, your uncertainty is bounded by your von Neumann entropy, right? Okay. Again, you see that these are additive. There are two different sources of uncertainty in the quantum world. One is quantum mechanical, which comes out of non-orthogonality, which comes out of the statement that observables are matrices, and generally they do not commute, namely that eigenstates of this observable are not generally orthogonal to this observable. It's a purely dynamical statement, right? And then there is another sort of uncertainty is that this is really ignorance, right? The density matrix tells you that you do not observe some things, right? You're only dealing with part of degrees of freedom. It's like more or less like in a classical system, this thing. And they come additive. And they bound something which is a kind of, you just measure x, right? You do just measurement on your momentum. You do measurement on your coordinates, right? In the same state of this. And then you, out of this many measurements, you see probability distribution, you compute entropies, and you know that this is bounded from below by the nature of this observable, and whether you are in a mixed state with respect to like everything else. So you trace the rest of the universe like this, okay? That's the end of quantum stuff. Think what you wanna ask, and think until the end. After the break, you'll tell me if you want me to write. Okay. I'll give you one more minute, and then we go to relativity. Maybe one more statement is just on a verbal level, but it's still maybe it's worth knowing because it's a very active field of research now. Is a thermalization. So let me discuss the last things about thermalization. Namely, coming to equilibrium. Is in the quantum world anything like this? Right? Because generally, when we were 19th century people and early 20th century people, we feel that thermalization or coming to thermal equilibrium is about this chaotic motion of particles which we don't observe, and so if we leave system alone, that more or less it kind of equilibrates other things. Okay? Now we say, I have a quantum system. Even if I consider it with an attached big system, it's still in a quantum state, in a pure quantum state. Is there any sense in which I can take a quantum system and say that alone it's in some state, in a pure quantum state, and then I attach it to the big thermostat? Let me put it inside. So this is the thermostat. But this thermostat is also a quantum system. Okay? And they together are in a pure state. But initially, no, maybe I'll make it really like I bring it and I attach it. So imagine that I have A somewhere here and a big B here, and then I bring it and attach A to B. They start interacting. Okay? And B is huge. I mean, like this room, which is still a quantum system, right? Believe it or not. In what sense I can say that this now will come to thermal equilibrium with its environment, and what would be the temperature? And the answer is yes. And it's surprisingly, or not surprisingly, related, of course, to the von Neumann entropy, because they say, look, this system now in a pure quantum state. As I attach it to B, and it starts interacting, and this interaction is a dynamical, unitary process. But there is more and more information about A would start to be encoded in B. Like when we said the last lecture about quantum measurement, your quantum psi function leaks in this Hilbert space in this many other directions. Okay? What it now characterizes? If you're still observing only A, not measuring anything about B, this would grow. Right? Because you will be in the end, this growth will saturate, and in which state it would saturate? It would saturate in a state where the density matrix of your things would be exponent minus beta Hamiltonian of your system A. And this is something which is very interesting to prove, and it's very difficult to prove for any real system. And a lot of people are now considering different particular cases. And in the book, at the very end, I guess, there is a small problem about it, how you can describe the beginning of this process, for example. You take like one spin, and then you attach it to a spin chain, and you see how entanglement propagates, how it gets in the more and the more entangled state, just evolving by its own Hamiltonian. So essentially, you show that your system evolves to the same Gibbs state. Now it's quantum, because it's a Hamiltonian is a matrix. So it's a matrix. Okay? It's a density matrix, and you can show that it has a maximal von Neumann entropy, etc. So in this way, kind of surprisingly, we see that all the standard things which we sort of in the classical thermodynamics are working in a quantum world, and of course it's a huge activity how really this thing grows and how system approaches the state. Okay, so when you see quantum thermalization, it's about this. It's describing purely quantum evolution, and yet leading to thermalization, to increase of entropy, and this entropy which increases is an entanglement entropy between the state. Okay? Information leaks out. It's preserved somewhere, but you don't see it. Okay? Good. So now think again for a minute, and we'll go into relativity. It's breathtaking pace. I'll give you quantum mechanics in 2 lectures and relativity in half. Like 1.5 lecture for quantum mechanics and half lecture for relativity.
I have a question about the. Yeah. So if we take x equals to z, like just the same operator, we get like.
Well, then.
When
x is equal to z, that means that there is this absent. Yeah, there is no. Yes. There is no non-commutativity, so your entropy is bounded by S of 1.
By half of S of 1?
Yeah, it's bounded by mixing. If there is no mixing, then it's not zero, it's bounded by 0. Okay. But if there is a mixing, it bounds. Okay. Good. So now relativity. First of all, what relativity tells us that the speed, well, essentially, the only thing that relativity tells us is that the speed is bounded by 0. First, it tells you that there are just casual causality horizons, right? That if something is at the distance which is larger than speed of sound times such interval of time, then you cannot know anything for this interval of time about this region. In the past, yes, but for this interval, no. So in kind of space-time, you can see some horizons which tells you, so these are hidden. And there is a second source of restriction which relativity imposes on us is that there are black holes. Okay? So generally, if you take a if you take any body with a mass m, okay, so you have a body having a mass m, and you have your own body with a mass m, so you have m times mg divided by r, where this is your r, and this is your potential energy. If you want to escape out of it and go away, then, well, like simply classically, then this must be larger than this, okay? But on the other hand, this must be less than this, okay? So it tells you that it's a restriction on R, right? So your R must be larger than something. R must be larger, and you see that M is helpfully cancels out. So your radius must be larger than G times M divided by C squared. And I won't write factors because in a moment I'll be, very hand-waving. You cannot escape from a smaller distance. Okay, it's just also some other restriction, some kind of a horizon. And every time that we see that there is some boundary or something hidden, there must be an entropy, right, which quantifies the degree of our uncertainty. So what kind of fundamental bounds we expect from relativity? Before I start telling it, let's try to imagine it. In quantum mechanics, what we get is S of x plus f of z larger than something, and there are two things. So we expect now some statements that the entropy of something would be larger than some fundamental bound. Or we can expect that the entropy of something could not be larger, must be smaller than some bound. Who thinks that we now will get something which will be bound from above, that the entropy is smaller than something, or it will be bound from below, that the entropy could not be smaller than something?
It usually bounds from below.
It's usually bound from below, which is a kind of a natural expectation. What else? And I'm not telling you what is correct. We'll have the whole break to meditate about it. What else we expect here? A little bit less trivial, namely not necessarily inequality bound, but relation between things which were before unrelated for us. Of course, we're talking about entropy. So try to imagine with what thing we would connect entropy in this relativity approach, with which it was not connected before.
Maybe some bound on transmission of information because of the...
One idea is that it's about the rate of information transmission. We used to think about capacity, how much, but now because there is a speed of sound, but it's a kind of a physical thing. It's okay, you can say, yeah, yes, probably that there is, if you put some kind of screen or boundary kind of area, information passing through this area could not be more than c, which has meters per second. How you get bits per second out of it?
Density.
I don't know, actually. This is a totally new idea for me, but I don't know how to turn meters into bits. Because I know how to turn joules into bits. It's done by temperature, right? So energy and bits are related to temperature. We spent 200 years, perfecting this connection. Maybe at some point, some of your generation will devise something fundamental which would turn your speed into bits. But it's not about this. What else? What we were discussing, that relativity creates horizons. Right? So you live somewhere here, right? And then you can always say that, look, there is this horizon, and this is c times t, right? So there's kind of some surface, and I don't see beyond this surface. And the moment I don't see something means entropy, uncertainty, right? So what we expect that now entropy will be connected. Distance. Okay, we're now talking meters. Yeah, meters is the right quantity to talk. Okay, but so now what we thought about meters per second, but now we're talking about meters. If we were talking about classical entropy, it's connected to distance, area, or volume. Volume. It was extensive quantity. You remember? Entropy, energy, total momentum, they were all extensive quantity, namely they behave like number of particles and the volume. What relativity suggests instead?
That the final thing we see is a 2D surface.
Yes. Now, if we don't see something beyond some surface, then our uncertainty may be not related how much volume is behind the surface. We don't know. What we do know is the surface, which we don't see. Right? Like in this, barnum circus or whatever. You see the surface, right? You don't know what is behind this. Okay? So opposite to what was in the classical thing, when we say, okay, we know the volume, we just don't see the molecules inside. So we expect our degree of uncertainty, entropy, to be proportional to this volume. And indeed, classical entropy is extensive, is proportional to volume. Now relativity suggests that if your uncertainty is related to the surface, then your entropy must be related to the surface. Because you don't know how much volume is behind the surface. Right? If you have its horizon, who knows what is in the, how big is the universe? You just don't know, sorry. You just see the surface. And this is the main surprise of relativity, and that's what we will be doing after the break. We'll derive the relation between entropy and surface. Okay? Good. And you now have 15 minutes to meditate on this. And also think if you want me to derive this terrible relation. You will find it in a book. But on the other hand, if you want, I'll derive.
I think it's okay. Oh.
Usually happens. Yeah, but indeed, it's about this.
Yes, okay, thanks.
Okay. The only way out is via black hole. Okay, that's how this section in the book is called. And believe it or not, it's the truth. There's no way out of this world. And if you go into the grave, it's not out of this world. Two things which relativity tells us. First is there are horizon in terms of unavailability of information, but there is even more dramatic horizon is in terms of a black hole. So what is a black hole? As we discussed, the radius from which you escape from a body must be larger than this distance. So now, if you have, and let's call this RH, it's apparently linearly proportional to the mass of the body. So if some body has a size which is less than the horizon, it's called black hole. That's the definition. Okay? Black hole is any object whose size is less than its mass times this fundamental thing. Okay? And so now suddenly we understand that maybe a black hole tells us, and relativity tells us something else. Not about that there are some screens for which there are some magic is hidden, but that there is a way to diminish entropy. Namely, you take your whatever you are having uncertainty about and drop it into black hole. Like Comrade Stalin said, no money, no uncertainty, right? So it's like it did not exist in this world anymore. And then what we would expect that the entropy would decrease. And that's a story about another PhD student, Israeli, who was passing, and his advisor told him that if I would just drop this cup of tea into a black hole, the entropy would disappear, and all this information about whether it was hot or cold, etc. And as Wheeler, who was also advisor of Feynman, said that the student was visibly disturbed by this statement. The student was Jakob Bekenstein, and 2 months later he came back to Wheeler and told him, no, you're wrong. You would increase the entropy of a black hole at least by that amount, which was essentially the following statement. The black hole has an entropy. Okay? And how you can make an entropy? Well, first of all, you need dimensionless number, right? The black hole is characterized by its horizon, which is its mass, essentially. But if you're just working within relativity, you have gravity and you have speed of light, and that's it. You cannot make dimensionless number which are bits. So what is, I mean, you always start thinking dimensionally, right? So what other Planck means you need to make this black hole quantum. It's already a huge jump, because for you black holes are classical astrophysical objects, and it's about gravity, and gravity is somewhere there, and suddenly you realize that probably quantum has something to do with it, and it makes the entropy of a black hole non-zero, and it saves our religious belief that whatever happens, uncertainty about world can only increase, cannot decrease. Otherwise, we would drop everything into black holes and live in a perfect harmony, So, why quantum mechanics saves the second law of thermodynamics, and what it has to do with the black hole? And why I'm telling it after von Neumann. About what quantum mechanics essentially tells us about the world in its most basic, thing.
It's discrete to some extent.
It's discrete to some extent, yes, but not in a sense that there are like points in space and nothing in between, right? But it also tells us something. Now we're talking about two regions of space. Black hole, okay, its horizon, and us, outside world, okay? And this idea, which Wheeler disturbed his student, was a separation of two these things. That if you take an object from here and drop it here, it's lost forever. Means that the horizon really separates. You cannot escape from inside the horizon. And who says no? Well, first, what law of nature says no? Of course, Hawking and Bekenstein. But I'm not asking about the name. What physical statement tells you that it's wrong to think about black hole as totally different from the outside world, totally separate?
Observation of everything.
Well, quantum mechanics say, but what quantum mechanics says about any systems A and B?
Certain.
Where this uncertainty comes from? What this delta P, delta Q tells you about physical world? Most important thing it tells you, no local measurements. There is no such thing as locality in quantum mechanics. Okay? Quantum mechanics, in its most basic mechanical sense, where everything is characterized by coordinate and momentum, tells you no way to separate region in phase space. There is P and Q. There's no way to say this is here and this is there. Right? And then it goes for all other physical variables. So essentially what quantum mechanics tells us that it's an illusion to think that black hole is completely detached from our world, because there is always an entanglement between A and B. And physically there are many ways to think about it. For example, one can think that kind of the physical mechanism is that the vacuum is not really a vacuum, right? There is always particle appearing for a short while and antiparticle at the same time because of conservation. Then they annihilate back and then they appear, then annihilate. It's kind of this quantum vacuum form, but imagine that such a pair would appear straddling a horizon. Okay? Again, quantum mechanics doesn't let you know right a boundary. Right? There's always something which h bar allows you, h bar divided by energy of this, let's say, electron-positron pair, h bar divided by this energy is the amount of time for which it can appear. Right? This is just uncertainty relation. And then what happens is that this is inside the horizon and it remains inside, but this is outside the horizon. Nothing prevents it from flying anywhere. Okay? And that's the idea of evaporation, or essentially a statement that the black hole has a finite temperature. That if it radiates, then it has a finite temperature. Okay? And so now we'll try to understand what would be the entropy of black hole, and for this we need to take energy and divide it by temperature. That's how you get entropy, right? So what is the energy of a black hole? It's some object with a mass. It's the only thing which characterizes it, it's its mass. That's it. You don't know anything else about it. Because what you see is its gravity. Gravity you feel, right? That's how we actually see the black holes, right? There's a black hole here, you see somebody just, feels this gravity. And this gravity divides the horizon, so you just as well can characterize any black hole by its volume of its horizon, because it's mass times this. So if you know that the only thing about object is mass, what is its energy? MC squared, of course. Energy is MC squared. There is not. It could be also rotating, having charge, etc. So there are many ways to add energy to it. But that's the most basic. Moment it has a mass, it has an energy. Now, what would be the temperature? Now that we know that there is kind of this thing, so there must be something, some temperature which is related to the fact that it's a finite object, right? So when you squeeze it, like you increase the space, the coordinate, it would be some kind of kinetic energy inside increasing or momentum increasing. So how would you estimate out of world constants and the only parameter of black holes? So you have a parameter, it's RH, or mass, it's the same. So how you can make temperature out of a size. Using h bar, of course. Now it's quantum phenomenon. Right?
Body radiation?
How? Well, technically, you say that this, it's also about some energy. Temperature now is in energetic units, right? So what is the energy that you can relate to a size? It's just like a size, and you have an h bar. What you need to take from h bar to joules or ergs. Frequency. What is the frequency that you can associate with a given size?
1 over r.
Times 6.
1 over r would be not a frequency, but 1 over centimeters. And you want 1 over seconds. So how to make 1 over centimeters? Namely, you already have
Multiplied by
h,
the speed.
1 over r. So we need, this is 1 over centimeters, and we need 1 over second. We need something which is centimeters per second.
The speed of light.
Or you can say that this is h ck, which is a frequency of a photon of which a wavelength is the size of your system. You can go low, right? That's kind of the longest photon is the size of your system. So now, if you say that this is your temperature, and the hc over rh, okay, and so now what you need to do is that you just say that my temperature is hc over rh, and this must be the derivative of energy of black hole with respect to the entropy of black hole, right? And the energy of black hole is mc squared, which is, you can always write m as c squared, and m is rhc squared, and divided by g. Okay, so this is c to the 4 rh divided by g. Okay, so we use a standard statement. The temperature is a derivative of energy with respect to entropy. Now it's a derivative of RH with respect to entropy, and it's equal to 1 over RH. Which immediately, now you can differentiate it. So your ds, if you put it here, is your equal to your dr and times r, h, rh, and it's c to the 4, and it's g, and what else I took, and then I need hc over here. Okay, so that's an equation. ds is drr, so it immediately tells you that your entropy of a black hole is equal to rh squared c cube gh. First of all, as you guess rightly, it's an area now. It's r squared, you see? And second, because it's dimensionless, apparently it's rh squared divided by what is called LP squared, and it's a definition of what is called Planck scale, which is Planck squared is just GH divided by C cube. And this is the first formula in our history in which all three fundamental constants, G, H, and C, appear in the same formula. It's still not any consistent theory of quantum gravity or anything like this, but at least this is a formula in which gravity and h bar appear together. H and C, they come together easily, right? It's general relativity. H is quantum mechanics. C is special relativity, right? H and C is quantum electrodynamics. So okay, I mean, we know how to handle two constants. We cannot handle three. And I believe that because we have two hands, and so maybe at some point there will be creatures with three hands, and then the brain would handle three things. But so far we only, okay? But first of all, what's really nice, that it's really area of a black hole, okay? And that's a unit, like I say, everything is discrete, so this is a unit, this is the cell. Cell is this Planck constant, and that's a famous Hawking-Bekenstein formula, etc. And now, what Bekenstein did on the next step is he say that now let's understand that the very existence of the non-zero entropy of a black hole means a bound from above on the entropy of any physical body. Okay? And that's an important statement that now I want to show you. Okay? So now we say let's say I have some body which has R and has inside energy E, and I'm asking how much uncertainty can I have about this region? Or in a more operational way, I'm saying, look, I can put here cold atoms, quantum spins, neurons, DNA, and how much information I can squeeze into this area. Okay? Then that would be my maximal measure of uncertainty is the same, and it's called information capacity. And it's not transmission capacity, right? Transmission capacity is how much I can transmit per unity, and here is just how much I can record in a given volume. Very fundamental question. Okay? How many bits could be recorded, encoded inside a given volume, using all degrees of freedom of physical system down to totally quantum, down to quarks inside my protons and all this. Okay, and apparently it's must be energy divided by temperature, right? And if there is an energy, but we already know how to relate temperature to the size, right? So we say that if I take energy and divide it by temperature, and if I define temperature in the same way, just by quantum uncertainty relation, right? So, this is E, and this is H, C over R, right? Then I would say that my entropy is probably bounded by this relation. And then Bekenstein, and for which he got all his prizes, etc., he actually says that it must be so, and it was not a result of hand-waving, of really of computation. What happens if you take this body and drop it inside a huge black hole with a mass m, and then this, whatever information you happen to encode here, would be hidden now inside the black hole, but the mass of black hole would increase by this amount of mass, right? So if I now do this process, that my black hole mass add to it E over c squared, right? How the entropy of black hole is related to its mass?
For the radius.
Quadratically, because the mass is RH, or RH is Gm over c squared. So we can put it here and say that this is Gm over c squared over LP squared. So this is another formula. So now, if my mass would be larger, then in the first approximation, I can say if this black hole is really huge, then the addition of it would be just 2m over c squared, and this would be delta S, of which I increase the entropy of the black hole. Okay? And then I say that my entropy must be less than this. Okay? And but this is something which, but on the other hand, it relates M, which is related to RH. But RH at least must be larger than the size of my body R if I want it to be absorbed, right? So when I write this, that S is less or equal to delta S of black hole, and this is something which is ME from here, I take it, divided by c squared, but then I can tell you that it must be, if I take M and express it RHC squared over G, let me first write inequality RHC squared C squared over GE, right? So this is my, I expressed M, mass of a black hole, so the radius of black hole, and now I say that this must be bounded by R E, if I put here R, over H C, where is my H here? Forget it. So I get this bound, but on the other hand, on this argument, the last really touch is the following thing. That of course, my RH must be larger than R, so that I would be able to drop this body into it. But on the other hand, this R by itself must be larger than RH of my E, or E over C squared, right? Because this thing must be itself not a black hole. If I can able to write information inside and read it from outside, then my R must be bounded by RH of E over C squared, which is GE divided by C to the 4. Okay? So when I take this Bekenstein relation and I take my E over here, bounded this way. So I would get it R squared. Instead of E, I substitute, so my E is less or equal than R times C to the 4 over G. So it's R C to the 4 over G H C, and it is of course R squared over L Planck squared. What did I derive? It's called Bekenstein bound. And it's a statement. Of course, you can also use it in this form, in terms of energy, but this is purely in terms of R. Because you have a given size R, you cannot encode there more information than R squared divided by Planck squared, which happen to be, what is the size of an object divided by LP squared? It's an entropy of black hole, which tells me that if you take any region of size R, maximum information is in the black hole of this horizon. This is the entropy of a black hole of this horizon. And this is Bekenstein bound on an amount of information that could be encoded. It's really important statements. Let's again reiterate what did we do. We said that a black hole is not really a zero entropy object. Quantum mechanics, namely this h bar in the denominator, makes its entropy finite. Then we say that out of our religious belief that no matter happen in this world, black holes really don't present escape out of it. Because they have their finite entropy, then any body dropped into the black hole would make its entropy information of this body removed from our world, but the entropy of black hole would increase. And we believe, and this is now a statement which we need to check experimentally, we did not prove it. We just claim that if whatever happens in the world, the uncertainty could not decrease, that means that inside any body cannot be encoded more information than the entropy of black hole with a horizon of that size. And it has big consequences, if it's true. In particularly, and this is the last thing which, it's essentially the last thing that I'm telling you in this course, because the next lecture next week will be a summary. It's what happens to the universe. Let's talk big. Let's forget about our small. So what actually happens with the universe? Just if we look around, since Big Bang and all this. How would you describe what happens?
We lose information.
Well, first of all, is the world is getting kind of originally when it appeared. Look, if disappearing of object inside black holes tells us something about information, then appearing of the world out of Big Bang might also tell us something about information. Originally, we know that after inflation, it was a very, very uniform world. Then it started to expand. And it was still very, very uniform, right? But on some big scales, what happened is called Jeans instability. Namely, if you take any large enough volume of gravitating matter, gas, for example, it starts to be unstable with respect to inhomogeneities. You create some region which is a little bit denser, and then gravity starts collapsing it, and the matter from less dense region would go to the more dense region, and that's the way you create galaxies and stars and all this. It doesn't look like increasing entropy. It looks like appearing order out of relatively chaotic state. And then, of course, these big stars would create supernova, and supernova start creating heavy elements. There's no other way to create, carbon or metals. They're all created in supernova. For this, you really need to take all the matter and compress it in a very small piece. It's a huge decrease of entropy, right? Because the moment that you start concentrating things into small regions, it's a huge inhomogeneity, which means that your probability distribution now has huge peaks and entropy is much less. What the hell is going on? Does the entropy, forget about universe as a big object, right? And maybe it is in a pure quantum state, which goes by its, in its serenity and evolves, keeping just any big piece of a world. Does it entropy increases or decreases? As we look just on all this galaxy, star creation, supernovas, all this stuff.
So it increases, but the small areas of small entropy that are there. I mean, like air conditioning. We have here some place which is cooler, and rest is getting.
It's a very good way of thinking. When we think that we cool this room, which we did, right? Doesn't mean that the entropy of the universe is less. It's actually more, because there's a lot of entropy which is just shown in it. So when we see this galaxy created, and then stars, where the entropy is gone. where's entropy is gone? Because they definitely have less entropy. Take the same amount of gas, on a megaparsec scale and put this mass into several stars and even galaxies, and its entropy is much less. Where the entropy is gone, it must be larger. No, we're talking about serious problems. If you think that.
So we had like one type of particles, and then they create some new particles. So we have more information because now we have more kinds of particles. Does it increase the entropy now?
I don't know what you mean by particles, but in a sense, we do create a new element, a new combination of.
Yes.
Essentially, we all have the same, element, the same quarks and gluons from which you create things. But yeah, we can create some regions for which there would be. But imagine that you just take a very boring set of neutrons and protons and electrons, and it's this weakly ionized plasma like everywhere, and it starts collapsing into just more dense objects. Okay? Definitely entropy looks like by the same gravity. Gravity is a very important. So it creates some big regions. Where is the entropy of the universe?
Black holes.
Yes. What we now believe, and this formula, in a sense, is our way to believe in it, that the entropy of any object is bounded by the entropy of black holes. Black hole is the most entropic object in the universe. And the same gravitational instability, which creates this very inhomogeneous distribution of matter, necessarily creates some sufficiently massive object, which when all the nuclear, this reaction creating all the things, eventually they will end, right? And our sun will collapse. Our sun is small, but the bigger stars, they all collapse into black holes, right? And that's what we believe is where the entropy of the universe, most of it is, right? And this is why it's so important, really in a big picture, that when you look at the universe, it may seem as if its entropy decreases because we see more and more structure. We're very structured objects. We could exist only because of gravitational stability, which created this galaxy, which created the solar system. The solar system actually created a star which gives us energy. And some very distant supernova created heavy elements from which we actually built our bodies. Right? And all this seems like a huge process of organizing things and increasing order. But there are somewhere black holes which absorb all this extra entropy. Question?
But you would still see structure formation in, let's say, a simulation, a perfectly classical simulation of a cloud of gas.
Oh, yeah.
So where's the entropy going?
No, I mean, locally, if you take forget about quantum mechanics. You take a classical system, you take a classical big enough volume of gravitating gas. Of course, it has just instability, and it starts generating local structures. Okay? That's it. That's true. What it tells you that it's not how our world operates as a whole. If you look at our world, such processes happen, but on top of it, any subsystem can be, actually what Jeans instability tells us is that a gravitating body large enough of a gas, say, does not have a stable deep state, no stable thermal state. You can imagine deep state, and then you create inhomogeneity, and it collapses into different stars, right? That's it, yeah. So this subsystem does not have a stable thermal equilibrium, and fortunate for us, we live in such subsystem, right? But a universe as a whole, by this, still increases its size. That's a hypothesis, but seems to be very plausible. Okay? So that's why I really wanted to finish on it, and the next week we'll try to more or less, on one foot to go all the way through the course, in a sense that something like 11 or 12 take-home lessons that I want you to remember, and then I'll explain you about the exam. Okay? And where is the entropy? It very much reminds you, it's type of what is called Fermi equation. You know what Fermi equation? It's like how many times you need to lick ice cream to take half of it. And Fermi usually answered like in 40 seconds. So this is a question which, but one famous, when they were doing nuclear bomb in Manhattan at one lunch, Fermi suddenly, like citizen, but where is everyone? And it was why we don't see extraterrestrial civilization, because his estimate shown that there must be more. So this question, where is entropy, is a type of a Fermi equation, right? So from time to time you need to stop and like ask, okay, where is everyone? Okay?